So again, I just want to double check. Homework is not due, right? Okay. Yeah, that's unfortunate. So yeah. So I'll say this now, but I'm gonna say it again later, just for you too, Alexia. If you would like to do the homework and have someone grade it, I will grade the homework if you want me to. But you, and then not that you have to keep any schedule, you can turn it in whenever you want, but you do need to actually, if you want that to happen, you actually have to do it. But I definitely think it's a good idea to do it. But it's kind of hard, right? If you're doing homework and like no one's giving you feedback on it, it's kind of like, well, maybe I'm doing the right thing, maybe I'm not. So offer is open to anyone. If you want to do the homework and have me grade it, you are welcome to actually like do it like you're doing a homework assignment and submit it to me, either virtually or in person. I will grade it as quickly as I can and get it back to you. So just for, sorry, 1 second here, for who's joining here, Daisy, welcome. Please do fill out the attendance form when you have a second. I was just saying to Alexia and Ryan here that if anyone wants to do the homework for Lee and have it get graded, I'm happy to grade it for you. You should just turn it in whenever you want to. So yeah, that's an open offer to anyone in Lee's or the other person's class. I don't know what the other person's doing because. All right. So let's go ahead and do some more stuff with differential equations. Let's talk about down Co-16C. Today is April 5th, right? Yeah. Let's talk about verifying solutions to differential equations. I will mention here, people often abbreviate differential equations as diffEQs because like writing differential equations is a lot to write. So yeah. So for example, we're not being asked to solve it, right? They're giving us usually the general solution, and then we're just asked to show that it actually is. Let's say for the differential equation, which is going to be y prime minus 3x squared y equal to e to the x cubed. We want to verify that y equal to x e to the x cubed plus c e to the x cubed is a general solution. Okay, so typically the way you do this is you kind of look at your differential equation, you see what variables, or I should say, what functions and what derivatives of that function are there. So I see a y and a y prime. That means I'm going to need to sub in both y and y prime into this thing. So I already have y, great, but I need y prime. So let's go ahead and find what y prime is. So let's see here. So y prime is going to equal, taking the derivative of x e to the x cubed, I'm going to have to use the product rule. So it's going to be the derivative of x, which is 1, times e to the x cubed, plus x times the derivative of e to the x cubed. I'm going to have to use the chain rule. And the derivative of e to the stuff is e to the stuff times the derivative of that stuff. So that's the derivative of e to the x cubed. And then for a constant times e to the x cubed, constant multiples just hang out. The derivative of constant times e to the x cubed is the constant times the derivative of e to the x cubed again, which is again going to be e to the stuff times the derivative of that stuff. By the way, Evelyn, here is the attendance form. If you would please fill it out when you have a moment. Thank you. Can you see that all right, Ryan? Yeah. I always feel like it's a little washed out, but it's fine. So now that we've got y and y prime, it's going to be kind of messy algebraically. But we're just going to stuff all that in for y prime, substitute that in for y, and then see that we really do have the left side equaling the right hand side. So my y prime minus 3x squared y is going to end up equaling, so y prime is here, all right, it's going to be e to the x cubed. I'm going to simplify this just a tiny bit. And I'm zoomed in a lot. How did I, you know what, I pressed a button that I meant to press a different button. Sorry about that. There we go. I was like, what's happening here? There we go. I wanted to be just kind of brighter. So y prime, I was going to simplify this as x times 3x squared is 3x cubed. So have a plus 3x cubed e to the x cubed plus c times e to the x cubed times 3x squared, and then minus 3x squared times y. And y is just this, x e to the x cubed plus c e to the x cubed. Again, right, there's my prime, my y. And now we're going to simplify. So really, I'm just going to distribute the negative 3x squared to each of these terms and get e to the x cubed plus 3x cubed e to the x cubed plus c e to the x cubed 3x squared minus 3x squared times x is going to be 3x cubed e to the x cubed, and minus that times that is going to be a minus c e to the x cubed times 3x squared. And then we see things canceling. Hopefully everything except for the e to the x cubed is going to cancel, because I know what the answer is supposed to be already. So the 3x cubed e to the x cubed cancels with the negative 3x cubed e to the x cubed, and the c e to the x cubed 3x squared cancels with the minus c e to the x. Oh my, that's a mouthful. C e to the x cubed times 3x squared. And so we do in fact get that this is equal to e to the x cubed. We didn't actually solve it. They already gave us the solution. We were just showing that the solution actually works. Questions? All right, I think it's probably worth, let's do one more. One more, and then I'll probably have it. Yeah, let's try another one. Let's say our differential equation is y prime equal to 2xy over x squared minus y squared. And our general solution is x squared plus y squared equal to c times y. Now I'm going to point, oh, sorry, you can't see it. Yeah, definitely let me know. Thanks. So this one is a little bit different than the previous one. In the previous one, they told us y equal to some function was the solution. We took its derivative, plugged it into the appropriate places, and it worked out. Here, we don't have y all by itself. And really, I mean, one could, but it'd be a non-trivial amount of work to solve for y here. So if you've got something that looks like x's and y's kind of all mixed up together, what we really want to do is just take the derivative of both sides straight away. So instead of actually trying to find y prime, so we can't really just find y prime. Instead, we're going to differentiate both sides of our solution. Both sides of x squared plus y squared equal to c times y using implicit. So we're still making the assumption, or we're always making the assumption really here, that y is a function of x. So when we take the derivative of x squared plus y squared equal to c times y, we're going to use implicit differentiation. So for x squared plus y squared equal to c times y, we differentiate. The derivative of x squared is 2x. But the derivative of y squared isn't just 2y. Right, it's 2y or y prime, either way. I like to write y prime because it's a little less, but either way is totally fine. On the right-hand side, the same sort of thing. The constant multiple just sticks around, but the derivative of y is just the derivative of y prime, or dy dx. So people like to say it's 1 times y prime. Either way is fine. So now I have to think about what I'm going to do here. So I'm trying to show that this is a solution to that, or verify that this is a solution to that. I guess, so sometimes it actually kind of just works out super nicely. I guess here I really do have to solve for y prime. Sometimes when you do this though, like you take the derivative of both sides and it works out perfectly. You're like, done. But here we should probably do the usual work of solving for y prime. So let's see here. So I'm going to bring all my y primes to one side. So 2x equals c times y prime minus 2y times y prime. Factor out the y prime. So 2x equals y prime times c minus 2y. And finally solve for y prime. So 2x divided by c minus 2y is equal to y prime. Now we're going to plug that back in to our differential equation as well as interesting. So this one's weird. Now we're going to plug in y prime equal to 2x over c minus 2y. So we're going to get y prime, which is, I literally was going to not write this, but we're going to get 2x over c minus 2y equal to 2xy over x squared minus y squared. It's a little tricky. It doesn't look necessarily true. So I'm going to try and make these look the same. And what I noticed and this is kind of where you can really go in a lot of different directions. Are these equal to each other? Well, I can try and make the left side look like the right side by multiplying the left side by y over y to make the numerators look the same. That's something that just pops out to me. That seems like a reasonable, or maybe a not unreasonable thing to do. I'm going to multiply by y over y. So now I've got 2xy over, if I distribute the y here, I've got c times y minus 2y squared. And I'm asking myself, is this equal to 2xy over x squared minus y squared? And then I have to be observant. Tricky is really, I want to say I have to be tricky, but observant is probably the more of word. If you look back here at our general solution, it is true that c times y equals x squared plus y squared. So what we can do is we can plug in x squared plus y squared for c times y. So now, I know it seems kind of weird, but I'm going to replace this with 2xy over, well, c times y is going to be x squared minus y squared. And then, oh, sorry, minus, sorry, I got my signs messed up here. That's x squared plus y squared. That's a minus, apologies. And the question is that equal to 2xy over x squared minus y squared? And the answer is yes, because the denominator is x squared plus y squared minus 2y squared, which is the same thing as x squared minus y squared. So someone said they're a little bit confused about what we're doing. What we're doing here is we're verifying that something is a solution to a differential equation. And I think you might have come in and missed the first example, so we'll definitely do another example here. This one's a little trickier than some other ones because it's not as straightforward, where you just have y equal to something. Yeah, Brian. That's a good question. So the reason I did it was because I noticed that I had 2x on top here, and I had 2x times y here. And so I was trying to make the left side look the same as the right side. So, but really it's not the way you would have to have gone. Well, because if you're multiplying by y over y, totally fine, just multiply by 1. You could alternatively multiply both sides by y. But let's do another more straightforward example, Evelyn, and I think that might help a little bit. Also, where did I put it? Sorry, I have a lot of extra examples over here. 1 second. I think I do. Yeah, there they are. Yeah. Let's see here. 1 second. To me, honestly, it feels like sometimes solving them with separation is easier than actually verifying something's a solution.
When you did the C, did you do like the x plus y squared equals c times y, then you divide y?
I didn't divide y. So right, like what I did, like are you talking about this part here?
Yeah.
So what I did was I looked right here. I said, oh, c times y, right? It's tricky. Is equal to x squared plus y squared. Let's look at another more straightforward example. So again, we're verifying. Let's verify, which just means we're going to check that y equal to the natural log of x plus c over x is the general solution to the differential equation. What have we got here? X squared times y prime plus x times y equal to 1. So just like the first problem, I notice in this differential equation that I have a y and a y prime, meaning I need to take the thing that I'm being told is the solution, y equal to whatever, and then take its derivative so that I can plug in both y prime and y. So we have y equal to the natural log of x plus c over x. Let's go ahead and find y prime. So we're going to have to use the quotient rule. So it's going to be the bottom times the derivative of the top, and the derivative of the natural log of x is 1 over x, and the derivative of c is 0. And then minus, then we do it the other way, the top natural log of x plus c times the derivative of the bottom, which is just 1, all over the denominator squared. And I would definitely simplify this because it's going to be easier to deal with. So I do a little bit of simplifying. X times 1 over x is just 1. And minus natural log of x plus c times 1 is just minus natural log of x minus c. Excuse me, because you have to distribute the minus sign. All over x squared. So then what we're going to do is we're going to plug in y, what y is equal to. So we're going to take this y equal to the natural log of x plus c, and we're going to substitute it in right there. We're going to take y prime equal to 1 minus natural log of x minus c over x squared, and plug it in right there. And then we're going to show that the left-hand side ends up equaling the right-hand side. At least that's the hope. It should work out. If someone ever says, verify this thing as a solution, as long as they didn't give you a wrong problem, it should always actually work out to be equal to the thing it's supposed to be equal to. So let's see. So if I plug that in, I'm going to have x squared times y prime, which is 1 minus natural log of x minus c over x squared, plus x times y, which is natural log of x plus c over x. I don't like to say it's equal to 1. I like to kind of do the work to get to 1, but either way is fine. So this is equal to, well, let's see, the x squareds cancel, the x's cancel. So I've got 1 minus natural log of x minus c plus natural log of x plus c. And yeah, things are going to work out. The minus natural logs and the positive natural log cancels. The minus c and the plus c cancel. And this exactly equals 1, as we wanted it to. So hopefully that gives a better idea of what we're doing. We're just taking the given solution right there and making sure it actually is a solution by plugging it into all the right places, or its derivative into all the right places. Questions about this example? For another one here. I know I haven't. Oh, problem again. All right, so this one's a little trickier, but very. Thanks, Ryan. Will the answer be 1 for all other? No, it can be different every single time. So let's look at a different example. In fact, I'm gonna let you all try this one on your own for a couple minutes. So I want you all to verify that, y equal to 1 over x, or you might want to write it as y equal to x to the negative first, is a solution to the differential equation x times y double prime plus 2 times y prime is equal to 0. So what you all need to do, and I'll give you a couple minutes, is to find y prime and then find y double prime, and then plug each of those things in and multiply it out and make sure that you actually get 0. I'll give you 2 minutes. Oh, I know what I should do. Also, in case you haven't all gotten it, here is the attendance form again. Please fill out when you have a second. You finish, Ryan? Cool. And work? Good. I mean, it should. Uh-huh. All right, Alexia, Daisy, and Evelyn, I can't check your work, but I'm assuming you are doing it. I'll give you another 20-ish seconds here, and then we'll work through it here. You obviously don't have to. Cool. But it's to your benefit to do so, I think. So you definitely should. Yeah. Okay. Close enough to 2 minutes. Let's double check. So it's easier to take derivatives if it looks like this. So let's say we've got y equal to x to the negative first. Y prime is going to be -1 times x to the negative second, because we're subtracting it from the power. And y double prime is going to be +2, x to the -1 times -2 times x to the negative third. So then if we plug those in, we're going to have x times y double prime is 2 times x to the negative third plus 2 times y prime is -x to the negative second. If we simplify this, so you could rewrite this. You don't really need to, though. When you multiply x to the first by x to the negative third, you just add the powers and you get x to the negative second. So we're going to get 2x to the negative second minus 2x to the negative second, and those totally cancel each other out. So you definitely get 0. Right on. Let's do one more, which I had all queued up. Oh, yeah, let's check out this one. Sure. Let's so let's verify that that's a little gross. Let's do this one instead. That y equal to I don't want that. Let me think for a second here. Yep. That y equal to 5e to the 3x is a solution to the differential equation y double prime minus y prime. Gotta make sure it works out. Sorry. Oh, that's a 3. That's what I want. Yeah. Minus 6y equals, actually, fine, equals 0. Let's do that. So we gotta find some derivatives. Interesting. So y prime is going to be, well, the derivative of e to the 3x is e to the 3x times 3. So we're going to get 15e to the 3x. And the derivative of that, we're going to end up multiplying by another 3. So you're going to get 15e to the 3x times 3, which is going to be 45e to the 3x. Ooh, things are looking kind of big. A little worrying. Well, let's check it out. So we're going to plug in what we've got. So I'm going to have 45e to the 3x minus 15e to the 3x minus 6 times 5e to the 3x equal to, well, let's see. In fact, I can even do this kind of a more fun way. If I factor out the e to the 3x, I'm left with 45 minus 15 minus 6 times 5, and that's definitely 0. That's equal to e to the 3x times 0, which is 0. Checks out. So verifying solutions is usually not too terrible. It can get a bit messy if things are kind of defined implicitly, but most of the time that's not what we're going to see. So I would say not to worry about that too much. Trying to look for other examples here that might have that, but there's really not a lot. Oh, there's that one there. Yeah. I suppose, okay, fine. I feel like I owe you guys one more example. Let's try one more implicit one, just because they're a little weirder. So let's say, yeah. So this is number 1, 5, 6. So let's say our different, I just don't want to pick one that's too easy, but I don't want to pick one that's too hard either. Let's try that one. Sure. So our differential equation is the following. Yeah, I don't want, not that one. Sorry. It's like, no, that's terrible. Our differential equation is the following. X plus y parentheses times y prime minus x plus y equal to 0. It's funny. I feel like I would, if it were me and I was writing this question, I would totally have written this differential equation just to make it more fun as x plus y times y prime equals x minus y. Not that you need to do that, but they're really the same equation. So that's our differential equation, and the proposed solution that we're going to verify is, where'd you go here? Y, so it's not going to be nice. It's not going to be y equals something. It's going to be y squared plus 2xy minus x squared equals a constant. That's our solution to this differential equation. Could we do more work and actually solve for y? Yeah, you probably could. Are we going to? Definitely not. So what do we need? Well, we need y prime. And well, here's what makes this kind of hard. We need y prime, but we also kind of need y. So this is where you have to just play with it. So let's at least find y prime. I'm going to take the derivative of both sides using implicit differentiation. Derivative of y squared is 2y times y prime. Really, I should say it's 2 times y to the first times y prime. And then for 2x times y, we have to use the product rule. It's going to be the derivative of 2x, which is 2 times y, plus 2x times the derivative of y, which is y prime. Finally, minus 2x equals 0. Yeah. So what's that? 0, because we're taking the derivative of both sides. Now, I'm going to do some work that's going to feel kind of dumb in a minute, but I feel like I should do it anyway, just to kind of show you how you would usually attack this if you don't see the thing. So we're going to solve for y prime. But notice I'm leaving myself some room because, well, you'll see in a minute. So we solve for y prime, I'm going to keep these terms on the same side. So I have 2y prime plus 2xy prime equal to 2x minus 2y. And if I solve for y prime, I have y prime times 2y plus 2x equal to 2x minus 2y, and then divide. Y prime equals, I should factor out the 2's as well. 2 times x minus y divided by 2 times, I'm going to write x plus y instead of y plus x. Good question. So someone wrote, someone wrote, 2 people wrote things. So let me address these questions. So first question, why do we multiply times y prime on both sides again? It's not that we're multiplying by y prime on both sides. We're taking the derivative implicitly. So when I take the derivative of y squared, it's kind of like if I took the derivative of x cubed plus e to the x squared. The derivative of that, when you have the derivative of something squared, it's going to be 2 times that something to the first power times the derivative of that something. Here, the something is our y. So I take the derivative of y squared, and this is like taking the derivative of y squared. I get 2 times y to the first times the derivative of y. That's why we're multiplying by a y prime here and here. Because when we took the derivative of y squared, we got 2y times y prime. When I took the derivative of 2xy, we use the product rule. So, right, if you're thinking of this as like your f and this is like your g, here's your f prime times g, and here is your f times g prime. And then the derivative of x squared was just 2x. So that's why those y primes are showing up in our differentiation. And then the other question here, why would we take the derivative of the proposed solution instead of the first equation? So the first equation already has derivatives in it. The thing is, we're trying to show that this thing is a solution to that thing. We can't really use this. We have to use this and manipulate that to try and show it's a solution. So we're saying this is a solution. Let's take its derivative so that we can have its derivative to then plug into y prime here. That's why we are doing it that way. And that's fairly typical. When you're given a proposed solution, if you need the derivative of y to show up, we usually start taking its derivative to get that y prime. So canceling those twos, we have that y prime is equal to x minus y over x plus y. And then I'm going to plug that in to my differential equation. So my differential equation, which was x plus y, my first one, this one here, if I plug this in to the differential equation, I'm going to get x plus y times y prime, which is x minus y over x plus y minus x plus y. Oh, that's going to work out. The x plus y's cancel, and you get x minus y minus x plus y, which is 0. Now, here's why this is a little silly. A little. If we had been a little more observant, we could have been done right here. If I divide both sides by 2, essentially getting rid of the 2, I've got y times y prime plus y plus x times y prime minus x equal to 0. And if I group these two pieces together, I've got xy prime plus yy prime minus x plus y equal to 0, or factoring out the y prime from those two pieces, x plus y times y prime minus x plus y equals 0. That would also have been a totally fine way to show this is a solution. It's kind of weird though. The ones where you don't have y explicitly equal to a function of x are just a little trickier in your mind to deal with, I think. Questions about any of that? About this one specifically, or any of the other stuff? You guys are asking good questions. I think those are excellent things to ask about. You good, Ryan? Okay. So again, showing something as a solution, not too terrible usually. It's definitely easier, I think, in the previous examples where like you just have y equal to something with x's in it, and you take whatever derivatives you need to plug into the other thing. So then I suppose we should, let's see here. Yeah. So let's talk more about the other side of things, which is more the solving of differential equations. Because that's really more of what we focus on in this segment. I know, so I should back up a little bit. 16C is kind of a big mishmash of a lot of different topics. We're going to spend like maybe a week or 2 at the most on differential equations, then we're going to totally change gears and do other stuff. So definitely be prepared to shift gears kind of fast. There's a lot of things we cover in this class, and it just feels kind of like, here's all the things we haven't covered in 16A and 16B that someone thought you should still know by the time you finish calculus. That's kind of, in my opinion, what's going on in this class. Sorry, someone wrote something else. So if the first equation doesn't have the y prime, would we be taking the derivative of the first one instead of the proposed solution? So to be a differential equation, the differential equation has to have at least some derivative of y. So it could be y prime or y double prime or y triple prime. I think we had one example, if we look back for just a second. Yeah, no, I guess not. Well, I can make up it. So let me make up an example. So let's say we want to show that y equal to sine of 3x, let's say c times sine of 3x is a general solution to y, let me make sure I do this right. Sorry, I'm making it up as I go here, so I have to be careful for just a second. Yeah, y double prime equal to 9y. I think that's right. Let me double check in my head. Yep, that'll be fine. Nope, sorry. I think I want a plus, sorry. Plus 9y equals 0. That should work out. I was off by a sign. So I want to point out a couple things here. Thing one, to the differential equation. So this is a differential equation because it has a function, or I should say, it has at least one derivative of our function. It doesn't actually have to have the function itself in it, although usually it does. But you can totally have a differential equation that doesn't have the function y, but it has, maybe has y, and it has at least one of its derivatives, which it does, y double prime. So the proposed, I should say, the differential equation has to have a derivative in it. So when I'm looking at my proposed solution, right, this is the proposed solution. I don't want to take more derivatives of this because it's just going to get worse. I'm going to take derivatives of this to try and make it fit into this. So if I look at y equal to c times sine of x, the first derivative is going to be, well, the constant multiple, sine of 3x. The first derivative is going to be c times the derivative sine of some stuff is cosine of that stuff times the derivative of the insides. And I would probably rewrite this as 3c times cosine of 3x. And then the second derivative is going to be, well, the derivative of a constant times cosine of some stuff is that same constant times the derivative of cosine is negative sine of that stuff times the derivative of the inside stuff. Or simplifying it, 3 times 3 is 9, negative 9c times sine of 3x. Okay, so now what we're going to do is we're just going to plug those into the differential equation to see if it's actually a solution. So plugging in y double prime plus 9y equal to 0. Let's see, we're going to get, so y double prime is negative 9c times sine of 3x plus 9 times y is c times sine of 3x. When I simplify this, yeah, it's going to work out. We've got negative 9c times sine of 3x plus 9c times sine of 3x. And that definitely is just 0. They totally cancel each other out. So I would say the first equation, or I should say specifically the differential equation, is always going to have at least a derivative in it. The solution, on the other hand, typically does not. The solution usually just has y's and x's, whether it's something nice like this where y is a function of x, or something less nice like this where you have y's and x's mixed together, but there still aren't any derivatives in it. But I feel like this was less of a problem last quarter. It didn't have like a lot more people in here. Anyway, so yeah, so this one here, right? This was our proposed solution without any y primes. We took the derivative of that to find y prime and then plug it in. Same deal here. Our proposed solution doesn't have any derivatives in it. Our differential equation definitely has to qualify it to be a differential equation. That's what the differential part of that phrase means. And then we take derivatives of our proposed solution so that we can then plug into the differential equation to see if it actually works. Okay. So why do we care about differential equations? Well, many things in life are naturally described in terms of differential equations. One example, which is going to require a little bit of writing, but I think we have enough time. Yeah. Let's look at this. Oh, I was going to number that. I knew I was doing something there. I'm thinking 6, sure, 7. Yeah. So let's look at an example. Let's see, there's going to be a few words here. The rate of growth of a town's population is proportional to the population. Which makes sense at a very basic level. If you've got more people, they're going to make more people. So right, as the town population increases, the growth rate gets faster. If the town's population is 50,000 people in the year 2000 and 60,000 people in the year 2015, find the population in 2030. And what I want to strongly emphasize here is that it's not a linear relationship. We can't just say, oh, well, from 2000 to 2015, the population increased by 10,000. So from 2015 to 2030, it'll increase by 10,000 again. You don't have the same amount of increase per the same amount of years because it's not a linear relationship. It's actually an exponential relationship, which we're going to see in a second here. So here's what we're going to do. Here's how we're going to solve this. We're going to say, we're going to let y, so you like to write y or y of t, y is going to equal the town population at time t. And I would probably do something where I said off to the side here, like the year and the time. The year 2000, I'm going to say is time equal to 0. And the year 2015 is going to be time equal to 15. And the year 2030 is going to be time equal to 30. It's usually good to say that the first year you're starting at is time equals 0. That's a typical thing we do. And so if y is the population at time t, we can write the differential equation that's describing the situation. The rate of growth of a population or of a variable is just the derivative of that variable. So our rate of growth is dy dt. Our derivative, that's the rate of growth of the population. Now, when you say the two things are proportional, what we're really saying is one of them is a multiple of the other one. That's all being proportional means. So we're going to say that the rate of growth is equals proportional to the population, or is a multiple of the population. So the k here is the proportionality constant, or the constant of proportionality. Proportionality. And y, of course, is just the population again. Population size. So dy dt, or y prime, is the rate of growth of the population, and y itself is just how much population there is at any time t. So then we're going to solve this, and we're going to solve this how we were solving stuff on Monday, by separation of variables. We're going to separate. So y is on the left, t is on the right. I'm going to divide both sides by y. So I have 1 over y. I'm also going to multiply both sides by dt. So instead of having dy over dt, I'm just going to have a dy here. On the right-hand side, I'm going to have a k times dt. Cool. Now we're going to integrate both sides. So we're going to do the integral of 1 over y dy equals the integral of k times dt. What's the antiderivative of 1 over y? Ooh, it's been a while, I know. It's the natural, well, it's actually the natural log of the absolute value of y. So what I'll tell you is we almost always just ignore the absolute value, because if you don't ignore it, things still all work out just fine at the end, and you can go back and say, well, I could have ignored it from the beginning, so I might as well. We can talk a little bit more about the subtlety of that later, but I don't think we really need to right now. So the antiderivative of 1 over y is the natural log of y. And the integral of k of a constant is just that constant times your variable, plus another constant. Right? We have, just like we were doing on Monday, we have to put the plus c somewhere, and we always put the plus c on the side that doesn't have the y. Okay, so now to solve for y, we're going to exponentiate both sides. So we're going to say e to the natural log of y equals e to the all of that. E to the natural log of y is just y. I'm going to break this up as e to the kt times e to the c. But e to the c is just another constant, right? If c is some number like 3, e to the 3 is just another number. So this here, we're going to just call this c0. And use c0 specifically because now we can write this in the way you might recognize it. This is going to lead us to say, oh, look, we've got y equal to c naught e to the kt. That is the formula for exponential growth. So when you hear someone say, or you read that the rate of growth is proportional to the population size or the amount of stuff you have, what that really means is we have exponential growth. This will always work out in this way. And then the rest of it is just kind of doing the algebra. It's not an insignificant task, but the important part to really see here is that this differential equation, dy dt equal to the constant times y, or the rate of growth being proportional to the population size, leads to the exponential growth model, which is cool. So, of course, I don't really have enough room to do this here. I can probably make it fit. So then if we're going to solve this, we're going to use the following information. So let's see here. So we have y equal to c naught e to the kt. And I like to make a little table when I'm trying to actually find k and c naught. So I've got my year, which I don't really care about, my time, which I do care about, and the amount of stuff I have, or the population, y. So my years are, or my times are 0, 15, 30. Yeah, I could put in the years too. Okay, fine. But then we were told that in the beginning year in 2000, the population was 50,000. And then in 15 years later, in 2015, the population was 60,000. And our goal is to figure out what the population actually is in the year 2030. I like making a little table like this because it helps me know kind of where I should be plugging what into what. So I'm always going to start with this first time equal to 0 data here for 21. Okay, we're almost done. If I plug this in, I'm going to get, well, y is going to be 50,000 equal to c naught e to the k times 0. If you have time equal to 0, one sec, we're almost done. If you have time equal to 0, then we're going to essentially just get that constant c naught to be equal to the starting value. That's why c naught is often called your initial population or your starting value or whatever. So e to the 0 is just 1. So we end up getting c naught equal to 50,000. Okay, and we should wrap it up here because people are trying to bust in the door here. Then we're going to plug in this information here. So now we have y equal to 50,000 e to the k times t. And then we plug in this and we say, okay, great, y is now 60,000 equal to 50,000 e to the k times 15. Now we have to solve for k, which is kind of a pain. Divide both sides by that. 60,000 divided by 50,000 just reduces to 6 over 5. It's equal to e to the 15k. Take the natural log of both sides. And the natural log of e to the stuff is always just the stuff. So we have the natural log of 6/5 equals just 15k. We're solving for k. K equals the natural log of 6/5 divided by 15. So now we finally have the full model for exponential growth here. We have that y equals our c naught, which is 50,000, times e to the k, which is this gross thing over here. Natural log of 6/5 over 15 times t. And then to finally answer the last question, we're just going to plug in t equal to 30. So the population in 2030 just set t equal to 30. So we're going to get y equal to 50,000 times e to the natural log of 6/5 over 15 times 30. Which you could either plug into a calculator or whatever. If you do that, you'll get, let me see, 5. You'll get 72,000, which is going to be 72,000 people. I think that's exact also. It's kind of neat. Yep, 72,000. There is a way you can simplify this without a calculator, but we're out of time, so we'll talk about that next time. Yeah. All right.